How should we then store the key? How to generate the keys? There are two problems. The first problem is randomness, and the second is the secure storage of keys. When speaking of TPM modules, let's imagine them as smart cards. Why are smart cards called smart? What tasks do smart cards fulfill? They store the key. However, the key can safely be stored on a floppy disk or a flash drive. Smart cards, which simply store keys, are certainly not smart. These are definitely dumb cards. You can also buy them, and in the past were extremely popular, since they were fairly cheap. The intelligence of the cards depends on the fact that they not only store the key, but also protect it, by not making it available on the outside. This card is to generate the key. Otherwise, it would have to download it from the outside, which it shouldn't do. In addition to this, it must also carry out operations using this key. For example, decrypt data. It does this so that the key would never have to be made available on the outside. If it fulfills these conditions, we can say that it's a smart card. The problem is, however, that this is quite simple and it should be a fairly cheap device. So a card may try to physically get the data or destroy it. These types of attacks are confirmed and have occurred many times. Bearing in mind what we said about smart cards, let's now look at the TPM module. TPM modules, example seen above, are standard equipment in most likely all contemporary portable computers and servers. The task of the TPM modules is implementing certain algorithms. They're different algorithms according to the manufacturer and type of module. In addition, these modules generate and safely store keys. They de facto do the same as smart cards, but we did not connect them to the computer from the outside, because they're soldered to the board. They're relatively safe there. Of course, you can try to remove the housing of the TPM module and connect a probe directly to its modules, conducting an analysis of performance, time, and power. The TPM module in BitLocker is not used only to generate and store keys, but also to verify the integrity of the computer. The point is that the TPM module calculates the signature of the computer's process registers. The first thing the computer launches is the old BIOS system. This system saves certain information in storage registers. We'll take a look at that in a moment. The TPM module reads this information and compares its hash to the hash that was previously saved. This means that a change to the integrity of the computer, for example, connection to a new hard disk, or even a connection to a USB drive, will cause that the integrity of the computer will not be confirmed. The checksum will not agree. This means for the TPM module that the BitLocker key stored on it is to be blocked and not made available to the outside. Let's take a look then at which storage registers are used by BitLocker. Registers 4, 8, 9, 10, and 11 are used by default. We can also ask for an additional check of the runtime registers. We can, for example, check the ROM memory register. We then risk that in the event to any changes of the memory, the checksum will not agree. We can also check the runtime register connected with the BIOS system. This in turn would cause a situation that when we want to update the BIOS system, we would first have to turn off the BitLocker encryption. If we do not, we don't encrypt the disk. We have some information which clearly confirms the authenticity and integrity of the computer. It checks whether or not it's the same computer, if it's trying to run it from a CD or a USB drive, if someone has not connected a disk drive to it, or whether someone has taken out a disk and connected it to another computer. As we mentioned, this information is vital to make a decision on whether or not the key stored in the TPM module will be decrypted. Let's now look at the keys in their hierarchy. We already know that encryption consists of encrypting individual disk sectors, the AES algorithm operating in CBC mode. This is a mode in which the encryption key to the next sector is derived from the previous encrypted sector. Encrypted data are diffused by elephant. Let's go to keys now. We have the storage root key. It's called SRK. It's safely stored in the TPM module. The volume master key, VMK, is encrypted using SRK. The VMK key protects BitLocker's full volume encryption key, FVEC. The point is that we need to be able to change the key without having to decrypt the entire disk with the old key and re-encrypt it with the new key. For such a solution to be possible, there must be an intermediate element. We'll be able to decrypt with an intermediate key and encrypt with a new key. This, however, will continue to be the same intermediate key which will decrypt the entire disk. Enabling and disabling BitLocker can be done very fast, regardless of how the disk is protected. Additionally, a copy of the VMK key is password protected, which we must provide when enabling BitLocker. If something terrible happened to our TPM module, we need to be able to return to our data. At this point, we can open the VMK key with a password, which we've saved or printed. The VMK key can additionally be protected by a smart card. Then you need to connect it when turning on your computer. Protection of the VMK may also be a combination of all these modes. The most commonly used mode, though, is the TPM module. In this mode, the mechanism of action is as follows. The BIOS system records the values of the PCR registers. It does this every time it's run. Based on selected PCR registers, the SRK key is generated. If the SRK key is valid, if the checksum was correct, it allows decrypting of the volume master key. In turn, this key decrypts the FVEC key already saved on the disk. The FVEC key is the primary key which allows decrypting other disk sectors.